Composite function is a process where we substitute functions inside another function. It's the same as doing any normal substitution, but you're going to be dealing with algebraic substitution, and we're using the formal definition of functions. And there are a couple of properties to note. One of them is that the range of the inner function becomes the domain of the outer function. That's something that is discussed in another video. But basically, this is the definition you should go with. I'll do a couple of examples and then I'll show a more formal definition of composite functions. So we can have different notations for composite functions. It could be something like f of g of x, like here. We could have g of f of x, so instead of the brackets, we'll use a circle. So it could be either way, so either using the brackets or putting the circles inside the bracket. All that it means is that you have to do all the processes in order. We start with the inner function first. And what you do is you're just doing the function substitution a couple of times. Either you're substituting an actual number like part d and f, or you're substituting just the variable x. Now, it might not make any sense unless we actually go through some examples. So I'm going to start with part d because it's much easier to see a number in there. So if I say f of g of -1, what that means is I'm asking you to substitute -1 into the function g first. Because if you noted, g of x is in the place of x, is in the place of this f of x, which means that g of x will now be the input of f of x. Well, I need to know what the input is. Well, my input, or let's look at here, my input is g of -1, so I need to actually calculate g of -1. So if you just isolate this g of -1, you'll notice that you just have to substitute this -1 into the function g. So I'm just going to substitute it in there, pretending it's a separate thing that I'm looking at. So this will be my -1, so everything will be, I'll substitute a -1 in there. Okay, and that's what we have here. This is basically g of -1. So you're going to do that process, and then it's going to simplify to -3. It means that g of -1 is equal to -3, and now I have f of -3. So I know how to calculate this. I'm just going to substitute -3 into my function f, and I'm going to get -11. So that's the process that you have to go through. It's just a matter of substituting. First, you start with the inside function first, and then you work your way outwards. And either you're substituting a number or a letter. So this would give me -11. Now, what if I want just a general way? I don't want to go through this double process. I want one expression where I could substitute any value in there and it would give me this -11. Well, this is where we compose the functions purely using algebra. So that refers to part A. So if I'm asking for f of g of x, so my input, so first I need to input in g. My input in g is going to be x. So I'm just going to put, instead of g of x, I'm going to use this x squared plus 2x minus 1. Because if my input is x, then that is my output. Precisely, that is my output. I'm not going to get a number because I'm not substituting a number. So then the input of f is going to be this whole expression. Go back to the beginning of the definition of functions. We did practice how you'd input an expression inside a function. So this is precisely what's happening. I'm inputting an expression inside of f of x. Now this expression didn't come from nowhere. It came from g of x. So I'm taking the f, and wherever x appears, I'm just going to substitute my x squared plus 2x minus 1. So notice how this was the input of f, or like the output of g of x. And I'm substituting in there. I'll expand out and simplify, and I'm going to get 3x squared plus 6x minus 11. Now, this means that this is a general expression for f of g of x. So f of g of x is now equal to 3x squared plus 6x minus 8. And basically what that means is, what if I substitute -1 as we did in that previous example? If I substituted -1 in there, so I'll get 3 -1 squared plus 6 -1 minus 8. You can pause the video and try that out. So if you substitute the value in there, you're going to get 3 minus 6 minus 8, and that is going to give you precisely negative 11. So exactly as the answer we did before. The exception this time is that now I have a general way of talking about f of g of x, whereas in the first method, or in the previous slide, it was more of a substituting twice, so doing it all over twice. A couple more examples. One thing to note is that the order matters. If you do f of g, it's not the same as doing g of f, and that's where we do part B. So again, it's the same notation, I'm just using a circle instead of a bracket, and g of f of x, this time my input is f of x, and the output of f of x is 3x minus 5, so this is basically f of x, okay, which came from here. So now this expression is going to be my input inside of g, so wherever the x appears, so this is my input, and my input goes here and here. So if my input is 3x minus 5, therefore I'm going to do 3x minus 5 squared, which I'm doing here, plus 2 times 3x minus 5, which is what I'm doing here, and then minus 1. So I'm just doing my substitution in there, and then I'm going to expand and simplify. Remember, this is a normal binomial expansion, so 3x minus 5 and 3x minus 5. Okay, just remember to multiply out. At some point, students do forget these basic math operations. You're going to expand out, simplify, and you're going to get this. So notice how 9x squared minus 24x plus 14 is completely different from this expression. It means that the order really matters for f of x and g of x. There are some instances where the order won't matter, but those are special cases that are discussed later. Now, what if you have three functions being composite with each other? That's completely fine. We can compose as many functions as we want. We can also compose the same function twice. Notice how it happens in part E if you want to try that on your own. I'm going to try part F, where it's f of g of h of 1. I particularly want this because h of x is a constant function, so it's a negative 3. No matter what your input is, your output will always be negative 3. So h of 1, again, we're going to compose h of 1 first. We start with the inner function. H of 1, it tells me, the function h tells me that no matter what your input is, your output is negative 3. So my output is negative 3. So then I'll have negative 3 into g of x, which is x squared plus 2x minus 1. So I'm just going to input that in there, and that's going to give me a 2. So g of negative 3 is basically a 2. And so this 2 now becomes the input of f of x. So f of 2 is equal to 1, and that's the final answer. So since we practice composite functions, it's good to put a more formal definition now. So basically, if you apply a function f to x, and it gives you f of x, and then apply another function g to your answer, you'll get g of f of x, or f of g of x, or g of f of x. Then you have applied the composite function g of f of x. Obviously, you can do it in any order you want, but the order matters depending on the question given. So you can use this arrow kind of thing. X goes into the function f, you get f of x, and then f of x becomes the input of g, and so you get g of f of x. Now, there are other ways to talk about composite function. One of them is using relations. So if I say find f of g of negative 2, that's the question. So I need to first find, we start with the inner function, I need to first know what g of negative 2 is. Well, remember relations, this is kind of your x and your y informally, so they tell you what relates to what. So you can clearly see that 2 relates to 3. So it means that g of negative 2 is going to be 3. And then we look at f of x, this is going to be 3, and it's going to give me an output of 4. So f of g of negative 2 is 4. If we did it the other way around, it won't quite work because we don't have negative 2, but obviously going back to the fact that order matters here. This is another way to compose functions, is to look at their graphs. You might have to compare different functions and you're graphing them, but you're meant to find the composite function. So you can pause and try this if you want to. Now, this graph has to be a bit more accurate, so we're just going to assume some of the values in there. We're going to start with the inner function g of 2. You're going to go at g of 2, and then you're going to go all the way to the graph that represents g, so it's here. And you want to know what the output is. So we're going to say it's 3. So I have f of 3. And then you're going to go at 3, which is here, and you're going to go all the way. This is your input now, and you're going to go all the way to f, the curve of f, and it's here. And you're going to see what output it's going to give you, and it's going to give you 3 again. In an exam or something, you'll obviously get more accurate graphs. Let's try one more. You can pause the video and try the others, or skip to when I reveal the answers. F of -1, you're going to go to -1. So first you're going to compose this, and you're going to go all the way to f, and it's about 1 here. So g of 1. So this f of -1 will give you g of 1. So now my input is 1, and I want to see what is the output on the curve of g. So I'm just going to go here, and this is the curve g, so it's about 2.5. Again, this graph is not that accurate. I just know that it would be 2.5. Let's try the last one, and g of 0, we're composing g with itself. G of 0 is going to be, well, we're here at 0, and I'm just going to go all the way to the curve of g, and that's going to give me 2, so I'm just going to get g of 2. And then my input is 2 now, so I'm just going to go all the way to curve of g, and that's going to give me a 3. So the answer is 3. Hopefully the video is useful. Make sure to watch the other video where I explain about the domain and range of composite functions.